Before understanding what the spectral theorem is, we need to understand the following ideas: what a hermitian matrix is, what a unitary matrix is, and what the Shear's decomposition is. A hermitian matrix is when the transpose conjugate of a matrix is equal to the matrix itself, such as an example such as this, where M is equal to 3, 2 plus I, 2 minus I, 4. The conjugate and transpose of it gives the same matrix, as you can see. A unitary matrix is when a square n by n matrix forms an orthonormal set, that is the column vectors, in the complex space n, where u1, u2, un are the column vectors. Let's say the inner product of ui uj is equal to delta ij, where delta ij is equal to 1 only if the vector is the inner product of itself, and if the inner product of itself of the vector with another vector in the same vector space is equal to 0, then we can consider these vectors as orthonormal. This is the property of orthonormal vectors. Now we move to the Shear's decomposition. Let's say we have a k plus 1 into k plus 1 matrix, where lambda 1 is an eigenvalue of A, such as ax equal lambda 1 x1, and we form a unitary eigenvector such that x1 over x is, we first find a unit eigenvector, and then we use the Gram-Smith process to find an orthonormal set of vectors such that w2 to wk plus 1 are orthonormal set of vectors for ck plus 1, for the complex space of ck plus 1. The first column of the orthonormal vectors multiplied by aw1 is lambda 1 e1, since wh into w1 will be the transpose of conjugate, so it will be w1 h transpose w1, which is equal to 1, but the other column vectors of w will be equal to 0, since it is not with the vector itself, because of the orthonormal property. Therefore, if you multiply wh aw, we would get a matrix such that lambda 1, we would get lambda 1 e1, and all the other byproducts of the other matrix of x of this, with an m which is a k by k matrix in beneath. Suppose we let v1 be a k by k unitary matrix of the property which is orthonormal, such that v1 conjugate transpose into m v1 is equal to t1, where t1 is an upper triangular matrix such as this. We let v1 is equal to 1 0 0 0, a diagonal matrix where v is a k by k matrix v1. Now when we multiply v conjugate transpose with the orthonormal, as you can see both are unitary, w and v are both unitary matrices. When we multiply them, we get an upper triangular matrix such that we can call T. As you can see, T1 is also a k by k matrix. Therefore, when we keep on multiplying, we're going to keep on getting a diagonal matrix with all the eigenvalues, and above the diagonal we'll be getting numbers which are the byproducts, and below it we'll be getting all zeros. Now we understand that T is equal to V conjugate transpose times W conjugate transpose into A WV. We let U equal WV. Since both are orthonormal, since both are unitary matrices, UHU should equal to the identity matrix. And we can prove that by using that UHU is equal to I. As we can see that WV conjugate is into W, we get WHW, which is equal to I, and VHV is equal to I, therefore proving that UHU is a unitary matrix. From this we can conclude that T is equal to UHAU, where U is an orthonormal set of vectors that is able to produce an upper triangular matrix, and vice versa as well. A is equal to UTU H transpose and conjugate. So moving on to the spectral theorem, the spectral theorem uses all these properties where U is a unitary matrix that diagonalizes A such that T is equal to UHAU, as we have seen before. Suppose we let TH is equal, we want to show that this is Hermitian, so we let T equal UHAU is equal to the same matrix, as we can see that because of the complex property, because of the property that ABH is equal to BHAH. Now if we use real symmetric matrices, real symmetric matrices have distinct eigenvalues, and if a matrix is a real symmetric matrix, then that means they can be orthogonalized into D equal Q transpose A Q, where Q is an orthogonal matrix and D is a diagonal matrix containing the eigenvalues. Additionally, it is also not a defective matrix. That's why symmetric matrices have real eigenvalues and real eigenvectors, as well as it is not defective. Now a normal matrix is when, if you see the real application of spectral theorem, we can see that normal matrices are non-Hermitian matrix because DH is not equal to D, meaning that if lambda 1 is equal to A plus IB, which is in D, then DH is equal to the conjugate of that. Transpose is not needed because it's on the diagonal. So lambda 1 conjugate will be A minus IB. Therefore, we will show that a normal matrix only satisfies the property of AAH is equal to AHA. Let's see of AAH. AAH is U D UH times U DH UH. As we can see, it's equal to UDDH UH. We get the same result when we apply AHA, as we can see that UDH UH times UDUH is equal to UDH DUH. Since DH is not equal to D, we can say that DH D is equal to DH since the lambda values will be squared and will always be a real number, because lambda 1, let's say lambda 1 is equal to A plus IB, and lambda conjugate is equal to A minus IB, but when we multiply them out we will always get a real number such that A squared will be equal to A squared plus B squared. From this property we can say that normal matrices are AH equal to AHA, and this is only true if the matrix is a skew symmetric where AT is equal to minus A, and skew hermitian where AH is equal to minus A. This is because additionally Jones should have the property that it can be diagonalized by an orthonormal set of vectors, eigenvectors, which is U.